The University of Western Macedonia is located in northern Greece.
Our region is one of the safest in Greece.
We cooperate with distinguished foreign universities. We welcome students from all over the world, and we're always striving to gain new knowledge and experiences.
Our region is the center of Greece's energy sector, and the university has a key role towards a future without lignite.
Here at the University of Western Macedonia, we always aim high.
Button. And in the meantime, I'm going to accept everyone that is in the waiting room. So, Marco, the floor is in you. I believe that no introduction is needed. Marco is one of the biggest names in the communication world. And all of you that are here, I am sure you know him and you're eager to hear him and not me. So, Marco, please.
Okay, thank you very much, Alex. So it's a great pleasure, to be with all of you. Thank you very much for this invitation and the opportunity to share what we are doing. In my group and also with some collaborators. So I will try to start sharing. Maybe, yeah. Can you see my slides?
Yes, we can see your slides.
Okay, good. So now I do this. Okay, and I will do like that. Okay, so as I was saying, so thank you very much. So Alex, so in this presentation, I will try to highlight some of the research works that I've been doing with my group and around the concept of intelligent metasurfaces or programmable metasurfaces. And the idea is to show you what there is around, but primarily is to introduce some kind of recent programmable metasurface that we have been discussing with Alex and his team, and that are emerging and that are quite promising, especially for enabling this convergence between communications, computing, and sensing. And there are some projects that more or less tackle this, and hopefully, some new ones coming soon on this topic. So it will not take that long. I will try to keep it within this 15 minutes, so we can. And I will be, happy to take any questions. So if you have any questions, just put it in the chat, and I will try to answer. So let's start with a quick recap on metamaterials, programmable metamaterials and metasurfaces, and then we go to the new part. So the way that what is this metamaterial or intelligent metasurface in wireless communication? Is essentially a surface where we have many antenna elements, and which are shown in red, and then some electronic circuits. There are no power amplifiers in principle. We would like to make it simple, at least the surface itself, and no digital signal processing done on the surface itself. Then I will be more precise. And the way that we see it in wireless communications is that this pair antenna elements, reconfigurable electronic circuits, operates as a sort of programmable phase shifter, where we can control the phase, and sometimes we can also control the amplitude, or somehow this phase and amplitude are not necessarily independent of each other. So the main thing is that we are capable of controlling the output, the reflected waves or the transmitted wave, by tuning this phase shift that are available in this coefficient. So now the one paper that you may want to look at, I will give you a couple, throughout this presentation. That's one of those. Here you will find some recent advances in this field, and which is also the first part of this presentation. So now these programmable surfaces, for those of you who may not be familiar with that, has been utilized for several applications. I will first review in general what kind of things that has been done, and then I will go more into the details of a couple of examples. So use of these programmable surfaces, the one that has been analyzed in most of the papers, is the so-called relay type intelligent surface, or reconfigurable intelligent surface, and this acts as a sort of a relay, but a passive relay, or at least a nearly passive relay. So the idea is that we get a signal, and then depending where the user is, we try to steer the beams towards the location of the users. This is especially true when the signal from the base station to the user is blocked by obstacles, for example. There are also applications to utilize these reconfigurable surfaces as a transmitter, so to transmit data. So imagine that you may have sensors, for example, on top of this surface. You send some data, and then you want to encode this data in addition to your reflection. So what you can do, for example, you could steer the beams in this direction, but you can also encode the data onto the elements that are switched on and off. This is a very simple case study. So by changing the on-off pattern, you can encode the data. And this allows you to implement modulation at a lower complexity. Another application is to embed these programmable surfaces at the transmitter. Here you have a conventional antenna elements, and then we could surround these antenna elements through these reconfigurable surfaces by optimizing the coefficients of these programmable surfaces. We can, for example, create a rich scattering environment. So imagine that we have a system where we have a strong line of sight channel, and so we may not be able to get spatial multiplexing gain if we have multiple antenna systems. We could create a multipath rich channel through this deployment. There have been also quite a lot of studies so the vast majority of studies assume that these surfaces are relatively simple, so they are nearly passive. Nearly passive means that we don't have power amplifiers and we cannot amplify the signal. But recently, there have been some studies in enhancing the capabilities of these surfaces by adding some simple power amplifiers or tunnel diodes, which allows you, since you can now amplify, you can reach a longer distances. So you can increase basically the communication range of your system. And this is also something that people are very much interested in at the moment. Most of the studies have been focused on surfaces that operate as reflectors. So basically, you have the transmitter and the receiver are located on the same side of the surface. But now there are a lot of studies on surfaces that can do both reflection and transmission. This is because if the users are on the other side of the surface, essentially they may not be served if you do only reflection. So with this dual function surface, you can increase basically your coverage, and you can serve the users located anywhere. So and then I mean there have been now studies in utilizing these surfaces as so-called holographic transmitters. Holographic transmitter means that we do have this surface, but then now we have it's not like here where the surface is far from the transmitter, so it operates as a relay, but the surface is essentially we have a bunch of feeders that are connected to the surface, and then what we would like to do is to transmit multiple streams through this surface by optimally configuring basically the phase shift and the amplitude across this surface. And there are also some implementations where you can have multiple surfaces together, and this we will discuss this in this presentation as well. So this is a very general overview to tell you that essentially these programmable surfaces have been, the vast majority of papers are focused on this case, relay type, but they have recently been proposed to do many things, transmission, changing the channel to create some multipath rich channel. They may not necessarily be passive, and also not only for reflection, but for enable multiple functionalities. That's essentially what I wanted to say. So in wireless communications, usually we are interested in solving these kind of problems, where we have, for example, a simple transmitter and receiver, and now the end-to-end SNR, so the SNR at the receiver depends on the pre-coding signal at the transmitter, decoding signal at the receiver, and then also we have this reflection coefficients that we can optimize here. Okay, so now we can optimize three variables: Q, theta, and W. And usually, a divisible set of theta, which models the RIS, the programmable surface in general, needs to account for some implementation constraints. So, for example, if the surface is not does not amplify, the reflection coefficient at most needs to be 1, and also we may not be able to implement all the possible phase shifts. So, these two sets are not convex sets, and therefore, I mean, the optimization problem is usually pretty challenging, and there are now a few algorithms that have been proposed to tackle them. Now, the mathematical background, I want to give you a very simple example because, in general, these problems can be solved numerically, but there are some simple cases where we can get some understanding of what the optimal design of these surfaces should be. So if, for example, we want to implement a simple reflector in a one single user system and a single user a single antenna transmitter and a single antenna receiver, we would like to steer this beam in green towards this direction in blue. We know that there is a law which is called the generalized Snell law that tells us that the sign of the angle of reflection depends on the sign of the angle of incidence and also the first order derivative of the phase shift that we can apply on this surface. And it's interesting to see that if we make this phase shift linear, we can steer the incident signal towards any desired angle of reflection by just optimizing this coefficient alpha. Okay, so of course, I mean, this does not tell us the amount of power that goes toward the receiver. This is another problem, but at least there is a simple rule that allows us to optimize this kind of phase shift applied to the surface, at least in this simple case study. So now the deployment of these programmable surfaces in a wireless network changes a little bit the assumption and the system model. So the first thing is that there are two main things that change in the signal model. The first thing is that usually these surfaces need to be large, especially if they are passive, if they don't amplify the signal. And this means that if they are very large, there are many users that may not be in the far field anymore, but they are in the near field, in the far field anymore, but they are in the near field, which means that in many communication systems now we utilize far field communication models, but these far field communication models are not good enough if we need to model the near field. So that's the first thing. And essentially here we clearly see this that if we make the surface very large in size, or if we move to sub-terahertz frequencies, for example, this boundary, the Fraunhofer far field, will move to the right, which means that many users that were in the far field now are in the near field. Another big point is that usually we deploy antennas spaced lambda over 2, so we try to avoid mutual coupling, but this may result in not utilizing in the best possible way the surface that we have at our disposal because we have a lot of empty space. We may put many more elements on the same space, but then we need to deal with the mutual coupling. And also we may want to keep to have the elements very close to one another, because if we do that, we may add the same number of elements here, 9, in a much smaller space, which allows us to keep the surface limited in size, especially if we want to apply it, utilize it to mobile terminals, for example. So now this is what basically exists. So now, if you want to know more about the fundamentals, about this, the changes in the signal models that this large surfaces introduces, programmable surfaces introduces to us, I recommend you to have a look at this paper, which basically deals about the fundamental theory that we need to know to deal with this with these structures. That's essentially the idea. So this is a paper published in the Information Theory magazine, which is a new journal that was established within the information theory community. So now, what the main part of this presentation, so this was just a general introduction, is really to now to go on to some recent advances, and I would like to show you a couple of new programmable surfaces that have recently been proposed, and then and now, I mean, people are really focusing on them. The first one is called the flexible intelligent metasurface, and I will spend a little bit less time on it. I will spend more time on the second one, which is called stacked intelligent metasurface, or SIM, or SIM, and because it is it's considered to be a very good platform for enabling communication, sensing, and computing, which is a very hot topic at the moment. So let's start with this flexible surface. So most of the programmable surfaces that have been studied so far, they are planar, okay? Because they are easy to deploy, they are simple to build. But there are many environments, I mean, many places where we can put these surfaces on a roof of a car, on a train, or even, I mean, we can have a structure of this type where the surface is not planar, but the structure is so-called conformal. So it's not really planar. So there is an interest on that. The other interest is that there are now some advanced materials that are also flexible. So we may be able to optimize not only the electronic circuits that control the elements, but also the position of the elements themselves. So for example, here we have the so-called morphic range, which is, for example, the the kind of flexibility that we can have in bending this substrate along the z direction. Okay. And this may allow us to have a further degrees of freedom in order to optimize the performance. This is called metamorphic or even movable surface. So there are examples of substrates in the literature that allows us to do that. Of course, there is, it's not possible to have any morphic range, so there are limitations on the flexibility of the substrate, but this, I mean, people are working on that. So now these are also examples of movable structures where you may deploy these reconfigurable elements on a curtain or on blinds, which can move. And this means that here this structure of the array is not anymore fixed, it's dynamic, and the performance depends on the actual positions of these elements, which can change over time. That's basically the point. This is really a technique to put these reconfigurable elements everywhere, also on surfaces that are not static, but like a curtain, which is dynamic, because we may want to close and open it. So now that's a little bit of some general things. Now I would like to show you some more scientific results and what kind of gains these flexible metamaterials allows us to get in wireless communication. So these are two papers. The first one study flexible intelligent surfaces for conventional communication models. In this second one, we utilize some more advanced communication models, and I would like to show you here, present you here the second paper, which is also available on arXiv, to try to figure out what the benefits of optimizing the locations of the antenna elements is with respect to keeping them static. So the first thing is how to model in a good manner this structure. So the idea is that we have a general scenario where we have a transmitter, multiple users, and then this flexible device where these elements can be moved. General conformal structure, and we need to get a model that allows us to express for example, the signal received at the receiver as a function of the signal at the transmitter. And the idea is to get this end-to-end channel model also by considering the impact of the multipath, so a general channel model. So we can first start with free space, which is much simpler, and then we see how to generalize it to multipath channels. The technique that we used is called the multiport network theory, which is an electromagnetic consistent approach for taking into account the actual electromagnetic implementation of these flexible metamaterials. The idea is that we model these flexible devices through electronic circuits. So one simple model that we use, just to simplify the mathematics, is that we assume that the reconfigurable elements can be modeled as dipoles that are connected to tunable impedances. The dipoles are fixed, and the tunable impedances can be optimized. And also, we assume that the location of the dipoles can be optimized as well. So the motivation of this modeling approach through the dipoles is because there is an approximation for general metamaterials, which is called the discrete dipole approximation, which essentially states that we may be able to approximate general metamaterials with a bunch of dipoles, provided that the dipoles are appropriately chosen. So if we use this multiport network theory, now I'm not going to show all the analytical derivations, but the concept is that you can actually compute this end-to-end channel model. And this end-to-end channel model depends on two things. On the tunable elements connected to the dipoles, and on the interactions between the dipoles. This is the so-called mutual coupling between the dipoles, which is the how strong the interactions, how strong the coupling between two elements on the surface is. This ZRIS can be diagonal or not, depending on whether we control all the dipoles independently, like in this structure, or whether we can control these dipoles also pairs of dipoles with other electronic circuits. And the mutual coupling on the other end, this matrix is full because there can be interactions with all the elements on the programmable surface. So, but long story short, this can be applied to free space, but it can also be generalized to multipath channels because any scatterer, any material objects can be approximated can be also approximated as a bunch of dipoles. That's essentially the idea. If you approximate as a scatterer with a bunch of dipoles, non-reconfigurable, so these impedances are fixed and they depend on the material properties of the object, then we can easily generalize this technique because we don't have only one FIM, flexible intelligent surface, but then we have also other surfaces that are static, that are fixed, but they can be modeled as a multiport system. At the end of the day, we end up getting a signal model that is similar to the one that I've already showed you, where we still retrieve the matrix of controllability and the matrix of mutual coupling. There is an extra term, which is this matrix here. This extra terms takes into account the impact of multipath propagation. It's in general a full matrix, but as you can see, the structure of the model, it's not that different from what we had before. The structure is essentially the same, with just one additional matrix there that we can deal with. So this is a general model that can be applied to free space, but also to multipath propagation, which is of interest for wireless communications. And this was also recently experimentally validated as part of a European project. So that's essentially the modeling part. Now, the interesting part is also the optimization. Why? Because now, when you can also change the location of the dipoles, you not only need to get the mutual coupling and then to optimize the electronic circuits connected to the dipoles, but you also need to optimize the layout. But the layout impacts the mutual impedance and also impacts the risk optimization. So you have a very complex problem where changing the location of the antennas, you change the mutual coupling, and this changes the optimal electronic circuits. So the problem, the optimization problems needs to take all this into account, and all these effects are strongly coupled with each other. So the typical optimization problem based on the model that I showed you can be formulated as this, which is this is nothing else than the received power, and this received power depends on the channel between transmitter and flexible surface. Then we have the channel between the flexible surface and the receiver, and then we have this part that I've already showed you. But now the optimization variable are the locations of the dipoles, which is this Q, and also the electronic circuits connected to the dipole, which is this vector B. Okay, and it's important to note that this matrix of mutual coupling strongly depends on the locations of the dipoles. So the way that we tackle this optimization problem is that we first, basically we can first optimize the electronic circuits, and we know how to do that by assuming that the locations are fixed, and then by assuming the electronic circuits fixed, we can optimize the locations of the antennas, and then we can iterate. And this is a typical alternating optimization problem. The first problem was already solved in the literature, and we provided an efficient solution to tackle the second problem. You will find also in the paper. So I'm not going to go much more into the details because I want to spend time on the other structure as well. But the idea is this now. This is the kind of results that we get. So the gray dipoles are what you get without optimizing the locations of the dipoles, but only the electronic circuits. And in green, you get the optimal layout when you are capable of optimizing the locations of the dipoles. You can see that there is that there are big differences between optimizing not optimizing the layout and optimizing the layout. And also there are quite significant gains because this is what you get without optimizing the layout, but only the electronic circuits. And this is what you get by optimizing the layout and the electronic circuits together. So you can get quite a few dB gains, which is not negligible at all. And this can be applied to linear arrays, planar arrays, cylindrical arrays, and also spherical arrays. So whatever the surface you have, basically this algorithm can be applied because it relies on a general model that is based on electromagnetic principles, on physical principles. So what I'm trying to say is that while in the past we were mostly looking at planar surfaces where we could not optimize the locations of the antenna elements, now we are looking at flexible substrates where we can optimize the flexibility of these devices, and we can get quite significant gains if we do that, because we have more degrees of freedom that we can exploit. So that's one of the topics that a few people are now working. Now, a second topic is the stacked intelligent metasurface, which it's something that now is picking up, and not only for communications, but for sensing and for computing. And I will show you also some experimental results. I will show you the first implementation of this device that is capable of doing communication and sensing at the same time. So what is a SIM? A SIM is a multi-layer programmable surface. You do not only have one layer, but you have multiple layers stacked one after the other. Essentially, each layer is a programmable surface in the way that I showed you, and then you just put many of them, one after the other. Why this? I will try to explain you why this could be beneficial for different point of view. But at a very high level, one of the reasons why this could make sense, and indeed this solution was initially proposed, is to mimic the operation of a neural network that operates not in the digital domain, but in the wave domain, so at the electromagnetic level. So you have a neural network at the speed of light when you do that without performing digital operations, so reducing the complexity, reducing the power consumption, and so on and so forth, as I will show you. There are some differences with the neural networks, which I will clarify in the following slides. So, but why SIM? So that's what it is. But why SIM? So it was initially proposed as a low complexity transmitter, as a low complexity base stations, but there are now also other applications as a low complexity computing device distributed throughout the network. Let's start as the benefits for utilizing it as a low complexity transmitter base station. The idea is that usually in a MIMO transmitter, we have a very complex baseband processing units, then high resolution digital to analog converters, and then we have the antennas. This costs a lot of money, this consumes a lot of power, and it's very complex to be realized because we have a very complex digital signal processing. A SIM, with a SIM, we can avoid or simplify a lot this baseband digital precoding and to move this digital precoding to the analog domain. As you can see here, there is no digital precoding. We just fire the signal to the RF chains, to the antennas, and then afterwards we do the processing in the web domain. The benefits are that we can significantly reduce the complexity, the number of RF chains, the power complexity, the power consumption, and so the energy efficiency, because we can reduce a lot of the digital signal processing. And we know that the power consumption, for example, of analog to digital converters increases linearly with the bandwidth, and now we are moving towards higher frequency bands and also exponentially with the number of bits. So we need to really reduce a lot the number of bits. And that's also the reason why many people are looking at 1 bit MIMO, for example, for similar reasons. But then there is also a second application, which is as a multi-layer processing device distributed throughout the network. This resembles to a relay or a reconfigurable intelligent surface, but that operates in at the electromagnetic level and through a multi-layer structure, so mimicking a sort of processing device, computing device, like a deep neural network. So the idea could be like that. If, for example, you want to enable communication between outdoor to indoor or between rooms at high frequencies, even a window may be a problem. But you may add here this device, and then this device may enable you to get a better communication between one side, the outdoor, for example, and the indoor, if you are doing outdoor to indoor communications, for example. That's essentially the idea. So we're used to this kind of systems. So to a system where we use reflecting surfaces. And the typical model that we utilize is that this surface is diagonal. So essentially, we are typically considering this kind of things where all the dipoles are controlled independently. Okay, that's the typical structure that we consider. But that's the point. Now, we are not talking, first of all, about reflection, but we are talking about refraction. So we are a device that lets the signal go through and processes the signal. But still, one may use diagonal implementations on each layer. That's essentially the point. Now, one of the main benefits of this multi-layer structure is the following. Even though, I mean, let's say this is the diagonal structure that I was talking about. One of the main things that we need to understand is that even though many people assume this as a structure, so the dipoles are controlled independently, information theory tells us that the optimal design for this, okay, the optimal design for a programmable surface is not this, is not controlling the dipoles independently, but rather we could try to maximize the capacity by imposing that the surface is passive, does not amplify the signal. And by solving this problem, I'm going a little bit fast here, but the idea is that by solving this optimization problem, it can be shown that the optimal matrix that you need to use is not diagonal, but it's a full matrix. So it means that if you use one layer with a typical diagonal structure, you are not doing the best from the information theoretic point of view. Okay. So why I'm telling you this? This is instrumental in order to understand the potential benefits of SIM. Why? First of all, non-diagonal means this, that rather than having this, you can also connect the dipoles, and therefore you can control them. So, but why I'm telling you this while talking about this SIM? The reason is that in a multi-layer structure, even though you model one layer with a diagonal architecture, so each layer here is the diagonal response, the point is that the end-to-end response of this device is given by the product of the transmission coefficient of this layer with the transmission coefficient of this layer, but also the propagation coefficient that connect layer 1 to layer 2. Now, the matrices T, which represents the transmission coefficient of each layer, they are diagonal. But the matrices of the propagation coefficient that connect one layer to another to the next, they are non-diagonal. So the end-to-end response is non-diagonal. So through this SIM, you could mimic this kind of structure. You could mimic a non-diagonal structure architecture by utilizing diagonal elements, diagonal metamaterials, which makes your implementation much simpler. That's one of the main things. Now, by using this model, there is one main difference that we can see with respect to deep neural networks, that this is a linear model. So we don't have non-linear functions like the activation functions that we have in a deep neural network. This is not inherent in the structure. This is an assumption that we make because we assume that this model holds true. But this model is very simplistic in the field of metamaterial. Indeed, if instead of utilizing this linear model, you utilize a more practical model, which is the one that I've already introduced to you, this multi-port network model, you will see that the response of each layer is not linear, because here you have an inverse of a matrix. So by using appropriate electromagnetic models, the response of each layer is non-linear. So in some sense, this structure enables non-linearity, and the assumption of linearity only comes from these simplified communication models. But we can enforce some non-linearities. Of course, we cannot completely control the non-linearities with this model, but the model is non-linear inherent. That's essentially one key point that we need to highlight. Now, SIM can be viewed as an efficient implementation for beyond non-diagonal structures with pros and cons. The disadvantage is that you have multiple layers. So when the signal propagates from one layer to another, there are attenuations. But you reduce a lot the number of circuits that you utilize. because you have in each layer you have diagonal elements and not a fully connected structure like this one. Okay, so you reduce the number of circuits, you reduce the implementation complexity, you reduce the power consumption. And indeed, in this recent paper, we showed that from the energy efficiency point of view, in blue you have what you can get with a non-diagonal structure, and in green what you have with a diagonal structure. It's not really always true that a non-diagonal structure is the best because of the complexity and the energy consumption associated with it. Okay? So these are the main motivations. Now, the benefits of multi-layer processing, this is an example that shows you that imagine that you have a signal and you want to focus your signal in this area, which can be a street in a downtown where the users may move. Okay, you want really to illuminate the street and make sure that wherever the user is, you get, or the users are, you can get only the signals there and you don't create interference everywhere. Well, if you have only one layer, you can get this kind of beamforming pattern. So one layer may not be enough to get the resolution that you can get for beamforming. If you increase the number of layers, this is 3 layers, you can already see a better shape. If you keep increasing the number of layers, you can get better performance. Of course, there is a diminishing return law. There are losses also that increase. The complexity increases as well, but maybe there is an optimal number of layers that can be chosen to trade off complexity with performance, but clearly the multi-layer structure could be convenient from the implementation point of view and from the performance point of view. That's one example. Another example is to, if, for example, we want to do beamforming. So if instead of doing digital beamforming, we want to do this web domain beamforming, what gains we can get? So that's we formulated an optimization problem to solve this multi-user MIMO problem in order to optimize the electronic circuits of the surface. I'm not going to spend much time on that. But the concept is that we solve this problem and by utilizing an algorithm which is based on the projected gradient ascent, which basically means that we find the solution iteratively. It's a first order, basically optimal solution where we take the objective, we compute the derivatives, and then we update the optimum by moving along the direction of the gradients. Okay. But long story short, I want to show you the gains. So this is the sum rate versus the number of RF chains. In blue, you have the fully digital solution based on zero forcing precoding, and in red, what you have with SIM. With the number of RF chains equal to 4, and with the number of configurable elements, which is equal to, let's say, 50 or 100. We see that if the number of RF chains is 4 for the digital solution, the digital precoding, you can get a huge gain thanks to the larger number of reconfigurable elements by keeping the same number of RF chains. You can even double basically your rate. In order for the digital precoding to get the same performance as a SIM, you need to have a number of RF chains, which is almost 2 times what you can utilize, you need for SIM. So you can really reduce the complexity. Okay. Also, this show, I mean, you can only look at the curve in blue, but here shows the sum rate versus the number of layers. You can see that there is a diminishing return because of these losses that we had when we have a multiple layers. And on the other end, we can see that if we increase the number of reconfigurable elements for each layer, we get a much better beamforming gain. Of course, at a given point, there will be a saturation that here we cannot see, especially when the mutual coupling will kick in. Okay, so This to show you that the multi-layer structure seems to have quite some good advantages, even though there are many issues that needs to be tackled from the implementation point of view, for example. Now, one of the questions that you may ask is, okay, but you are telling me that we are moving from digital to analog processing, but analog processing came before digital processing, before everything was analog. So basically, it's not clear whether we are moving forward or going backward, okay? But the concept is that the people have analyzed this, and also there are people expert in metamaterials that in the past, recently, proposed analog signal processing based on metamaterial devices as a possible complement to digital radio systems. So the reason why this didn't fly at that time, it might be because of implementation issues. But now we do have these powerful platforms, so this may be the right time to start looking back to analog processing in the web domain in order to reduce the complexity and the power consumption of our system, considering that sustainability is one of the KPIs that we need to consider today. One of the main things that we can do with these surfaces is not only communications, but also computing. Imagine that you have an input and you want to, while the signal propagates through the surface, through this multi-layer structure, you want to have at the output the bidimensional discrete Fourier transform of the input signal. You could utilize that to do, for example, direction of arrival estimation. That's an example that I want to show you. So the idea is that you can get the 2D bidimensional discrete Fourier transform if you optimize the transmission coefficient of this structure such that you mimic the matrix of a DFT. And this is the matrix of a DFT. So what you would like to do is to match your objective, your target, the DFT matrix, with the end-to-end response channel matrix of this SIM. That's what you would like to do. The way to do that is solving a minimization problem where you try to fit G with F. Fitting G with F, it's very similar to what we do with deep neural networks. We try to approximate some functions, and that's also the reason why deep neural networks are viewed as universal approximators. Okay, here we're trying to do the same, but we're trying to do the same in the wave domain. So this structure is a computing device that computes the DFT given an input. And I mean, long story short, but if you have a target and then you can sense this target along multiple points, and then given these points, you can compute the DFT of this sensed power, then you get the angular representation of the input data. So you get how the power is distributed in the angle domain, and from it you can compute the peaks, so the largest amount of power across all the directions, and you can try to do DOA estimation. That's what we did in a paper, and this is an example when you have only a 2x2 receiver, where you can clearly identify the direction of arrival with some error, because we don't have a lot of resolution with only 2x2 receiver. But if you add more receivers, you have a 4x4 receivers, you can increase the resolution. These are for different angles, and you can get a much better accuracy, and we can reduce the estimation error. So that's essentially the main signal processing part. Now, in the last 5 minutes, I will try to show you the fact that this device exists, and indeed we collaborated with a team of people in China who built basically this multi-layer structure for both communications and for sensing. So you can see here that they built this. This is one layer, and then we stacked these multiple layers one after the other. We optimize them, and then we try to see what performance we get numerically and also with the experiments. So If you are interested in the paper, this is the paper, which is already available on archive, and it was submitted for publications to Globecom. We are now working on a journal paper where you will find more details. The bottom line is that what we did in this paper is that we have a SIM, and we would like to do two things: communicate with some users and detect some targets. Okay, and what we solved is an optimization problem where we minimize the Kramer-Rao bound, subject to some communication constraints in terms of minimum SI and R at the users, with the typical total power budget and etc. So that's basically the problem that we try to tackle. We solve this problem. I'm not going to spend much on that because the mathematics is a bit tricky. But just to tell you that the experiments are obtained with this setting, where we have a multi-layer structure that operates at 5.8 GHz, so in the sub-6 spectrum, and each layer is a diagonal matrix, which creates a non-diagonal matrix as a cascaded channel, and also we have 1 bit control on each element of this surface. Okay, so it's extremely simple, but we try to leverage the multi-layer structure to get better performance. So these are the results obtained numerically. Then I will show you the experiments. Moving from here, from the bottom to the top, we are increasing the number of layers from 1 layer to 7 layers. And we can see that we can expand, so we can reduce the sensing error, and we can increase the SINR. So there is a quite a good benefit in adding layers, because we can get a better sensing accuracy with also a better SI and NR, and also some achievable values that otherwise would not be possible. Okay, that's because each layer is simple, and concatenating multiple layers, we can exploit this multi-layer gain. Now, these are the results obtained with the platform. So here we received, many questions usually when I give this presentation on, besides how many layers should I use, but also what should be the distance between the layers. Should I use layers lambda over 2, larger than lambda over 2, much smaller than lambda over 2? If I use very large layers, very large interdistance, then I'm going to have a lot of attenuation. And the structure is huge, is thick. But if I have close layers, then I have a strong mutual coupling. So we need to understand what the gains, what the optimum is. And indeed, it's not trivial at all here, because if the layers are spaced lambda over 4, by increasing the number of layers, we can clearly see a gain. If the number of layers are spaced lambda over 2, we can clearly see a gain. If we space the layers lambda, then things get problematic, okay, because the losses increase too much. The same if we keep increasing even further. So the blue line and the red line tells you what happens for lambda over 4 and lambda over 2, and the others tells you what happens for greater than for lambda and greater. You can really see that having multiple layers is beneficial if you properly adjust the interlayer distance. Otherwise, it's not beneficial. You can also see the big gain that you get when you have one layer compared to not having the layer at all. Okay, so here from not having a layer, you go from -70 to -57. And then adding layers, you can go from -57 to -46, something like this. As basically we can see here, and it's pretty good. Okay. Sorry, for 50, I was saying 50, 53, not 50, 57. Okay, it was on the other side. So yeah. So that's one thing. In terms of sensing performance, we can see that for given locations of the transmitter, by increasing the number of layers, we can increase the sensing accuracy. So we can get a better sensing accuracy by reducing the error, the sensing error in general by adding more layers. Except for this case, which is not totally clear, but in general, I mean, we can see that we can really increase the sensing accuracy. So the multi-layer structure seems to provide good gains for communications and for sensing. And this slide and this slide are obtained by utilizing the platform. So even though we are considering sub-lambda interlayer distance, we do consider decoupling between the elements because we are using the platform. There is no assumption on the model that we are actually considering. So this is an interesting result. So that being said, I try to close here since we are more or less reaching the time. If you are interested in this SIM, these are a few papers already available on internet. And it's a very recent field of research like FIM. If you can see here that the first paper were published in the mid of 2023. So it's less than 1 year, more or less 1 year that this idea is around. So there is truly a lot of things to be done, many really interesting problems at the intersection of communication, sensing, and computing, and also to take into account some electromagnetic characteristics and also a lot of implementation and measurements if you are if you are expert in experimental work and if you have the facilities for doing that. Yeah, so I mean, if you want to have another general paper where we discuss many of the things that I told you, this is one paper, which is the guest editor paper that we submitted for publication to a special issue in JSAC. The title of the special issue is exactly the title of this paper here, where we discuss all these emerging architectures. So with that being said, I mean, most of these activities are funded by European projects and already running, and hopefully some new projects under evaluation, and also by this very large national funded project, which is very large, where you can see here from the numbers, where there are many people in France working not only on what I told you, but this is part of this large projects. So with that, I would like to thank you, all of you, and especially Alex for the kind invitation, and happy to take questions, I mean, and to discuss with you. So thank you very much.
Thank you very much, Marco, for the interesting presentation. I see Abed, if I read it correctly, wants to make the first question. So,
hello, can you hear me?
Yes.
Thank you for your wonderful presentation, Professor Renzo, and thank you, Alex, for your nice organization. Professor Di Renzo, at the beginning of your presentation, I think in slides 5 and 6, you talk about that application of ARIS in which ARIS is used for modulation, right?
Yeah.
Actually, for space shift K modulation and reflection phase modulation and frequency reflection modulation, and recently in 2023, I saw in one of paper published in IEEE Transactional Wireless Communication, in which ARIS is employed for shifting the carrier frequency from the millimeter band to the sub-6 gigahertz, okay? Actually, in such systems, we have to use the cascade connection of passive dual bandpass filters along with the attenuators, along with the time varying terminations. I think these things cannot reduce the complexity, but through the SIM ARIS, maybe the complexity can be reduced. Am I right?
Yeah, I mean that's a very good point. Yeah, I think you are totally right. So in the sense that that specific application that you mentioned, so where basically we are doing this frequency conversion, it's much more challenging to do than what I told you, and the architectural structure would be a little bit more complex. Definitely, I mean, so SIM could be a way, I mean, to try to tackle it. We need to see, honestly, I mean, we need to see how this SIM operates at different frequencies. So we need to really try to figure out. But we could try to see whether there exists a mapping in the way basically that I try to discuss like this, where we could try to see a kind of matrix transformation that enables what we were saying, and then try to see how this could be meshed to this. We need to consider the frequency dependent response of the SIM. So this will be even more challenging to do. But I mean, we could try. That's definitely something that could be a sort of processing that we can do that deserves that could be very interesting. Very interesting, I mean, to be done. Yeah. So you make a very good point. So yeah, the kind of transmission-based techniques that I was discussing were much more easier. Yeah, definitely in that case you can reduce the complexity. The example that you provided is it's much more challenging. Yeah, it's not guaranteed that you will reduce the complexity. That's, I mean, for sure. Yeah, something to be studied. Yeah, that you make a very good point. Yeah, that's a good thing to analyze. Yeah, yeah. Thanks.
Thank you for your insightful answer.
Yeah, thank you very much. Thanks for attending. Yeah.
Marco, there are a couple of questions in the chat for
Yeah,
Mariam.
Yes, good. Okay, so let me see. Okay, thanks, Mariam. And there is written, thanks on slide 95. How do you justify the introduction of beta into the presentation problem? Yeah. So that's a good point. So beta is yeah, that's what we discussed in the. Let me see what it is. Yeah, it was here, 295. So that's a good point. What you say. So essentially, this beta, we discuss it in the paper. So written in this way, we may have the feeling that it's some kind of scaling factor that we apply on the incident signal, something like that. That's not the case. So we don't really apply this beta into the in practice. Beta is just a parameter that we introduce in this optimization problem in order to make F and G consistent from the scaling factor point of view. That's basically only the thing. When the system is operational, we just let the signal go, and then we basically apply the transformation based on the coefficients that we get. So there is no additional, basically additional scaling factor that we apply or operation that we apply on the incoming signal. This is something that basically we discussed in the paper. But I was not able to, I mean, because of time, to go much into the details. But that's a very good point. So this is just a scaling factor to make the two things consistent. But this is not something that you need to apply in practice on the incoming signal. So this is that's very important. Otherwise, it will become more complex to be done because you may attenuate or amplify, which could be problematic from the implementation point of view. Yeah. So thanks for this. That's a very good point. And then through the you say, I'm wondering through the implementation of SIM, did the theoretical modeling of the SIM have been justified? A specific interesting justification. Yeah. That's a very good point. So yeah, so so in simple terms, are this theoretical modeling of the SIM being justified? In a sound manner, the answer is no. So that's one of the big points that I'm working on. So you raise a very good point. This model that we use, the Sommerfield, I mean, there are, I mean, is good in the sense that, we take into account the fact that there is this cosinusoidal factor that accounts this angle of this obliquity factor, which is already something. We take into account the attenuation, but we don't take into account the mutual coupling between the elements. We don't take into account the insertion losses. There are many things that we don't really take into account. We don't take into account the nonlinearity of the response of the surface. So there are no experimental validation that tells us that this is a good model. It's just reasonable at the moment. There is a paper written by Bruno Clerks, and I'm also working on that, where it was applied this multi-port network model. So this model here. This is more accurate, but still, I mean, there are no experimental validation. So what I'm trying to say is that the only thing that I can tell you is the following from the experimental validation is that this model here assumed the simple linear model. We did the optimization of the SIM based on the Sommerfeld propagation. We optimized the SIM, and then we input this optimization onto the hardware platform. And the results that we get are not so bad, but we cannot claim that they are the optimum, because the Sommerfeld model may not necessarily represent the reality of propagation in this structure. So you raise a good point. So the development of electromagnetically consistent models for SIM is a huge problem, along with many practical questions that now many companies are asking, but nobody knows the answer. So I think that it will take a while for us to write down these problems and to try to find solutions to understand them. So this is something that I'm very much interested in, really, to try to find good models for SIM that are sufficiently tractable, but also sufficiently accurate to take into account the coupling, the insertion losses, the non-linearity, and so on and so forth. So I mean, your question is very good. So at the moment we are not that far. So it's but this is really the research problem that I'm working on. So that's what I can tell you at the moment. So I feel myself a little bit more, comfortable after we obtained these results with the platform, but still we miss the theoretical foundation. So theoretically, to be able to prove what is the optimal intra-layer distance, for example, that's we don't really know. So I'm more comfortable now that we have the platform, because at least it works in practice. But I mean that there is a lot of to be done. Yeah, that's so your question is very good. I mean, from that point of view. So the answer is, I mean, I hope that it is sufficient, but the answer is that it's really a work in progress at the moment. Yeah. And what SIM do you also introduce? This is Richard, I guess. You also introduce multipath. With SIM, you also introduce multipath, so that you have to equalize at the receiver. Or can you still assume a narrow band model without wondering about inter-symbol interference? Yeah, so that's, I mean, yeah, that's a good point. We don't know. So I mean, the model that so I mean, honestly, I mean, also, I mean, let's put it this way. Assume that there is this problem. So let's start from this point of view, because you raised a very good point. So let's assume that there is this ISI. Let's assume that we need to build an equalizer, but you could build an equalizer in the wave domain. So if this exists, now this has not been studied. I cannot tell you, because so far we just did this DOA estimation in terms of processing. But to me, the nice part could be, let me try to clarify what I'm trying to say. So imagine that we have that, no? So imagine that we have this problem. You could implement a SIM, also the receiver, so you could do equalization in the wave domain and then fire it at the receiver. So that's a very interesting problem. This could happen, but you could do the processing in the wave domain. So you would do beamforming, multi-layer beamforming, and multi-layer equalization, and try to optimize these two things jointly and try to see what is the best design. So from this point of view, I think that what you raise is a very interesting problem to try to see what happens at the receiver rather than only at the transmitter. Now, The models that we consider so far, we didn't really have gone that far. The propagation, the model that we consider for the propagation is very simple inside the SIM, and the models that we consider outside is basically the conventional one. We do have also model with multipath, but the multipath is modeled through a conventional statistical model. That's basically what we do. We have shown that things works, but still we are not able to connect, the electromagnetic model of SIM with the statistical model of the multipath. So this requires much more, a lot of study, in my opinion. But if you use a multi-port network model, the multi-port network model, you can model the multipath. So inherently, they should be consistent. That's the reason why we are trying to utilize the multi-port network model. So, but that's, a good point. In any direction that you see it, whether this exists, it's an opportunity to do equalization in the web domain, but we need to see exactly how to model this effect. So that's my answer at the moment. With the knowledge that we have at the moment. So I hope that more or less it's acceptable.
Thank you for the answer. Nice. Thank you for the answer.
Yeah, thanks, Richard. Yeah, thanks a lot.
It explains.
Yeah, cheers. And then we have a question from Majid. Thanks. What are some of the challenges in developing stack traces? Yeah, you mean yeah. So the challenges are many. So the first thing is that I can tell you some of the things that the companies told me, and we aim to work together, hopefully. So the point is, I think that it's a bit challenging that companies will believe or will assume that we can completely avoid the digital part. I think that what they are looking for is a solution where you can do something in the digital domain and then you can add this analog processing. So the point is really to figure out what is the best compromise between digital and analog in terms of complexity, bit reductions, etc. The other point is that this structure is very close to the antenna elements. So you are in the near and near field of this structure. So you need to also take into account the impact of how you illuminate this structure, because you need to illuminate the structure, which can be very large. So there is an illumination efficiency. There are of course, the propagation losses, but the insertion losses that you have. The other problem is how to model the fact that when the signal propagates inside the structure, if you don't match very well one layer with the next one, you may start having signal that enters into one layer and then is partially transmitted towards the other layer, and then some signal that is reflected back. So you start having some, transmission and reflections inside the structure that you need to control. That's for the moment is not basically considered because all the models assume that your transmission coefficient is equal to 1. So inherently, you don't assume backward propagation. Also, you assume that the decoupling, it's not decoupling, yeah, the transmission is from one layer to the other, but not throughout all the layers. So all these things, from the modeling point of view, are not taken into account. The other problem is how thick this structure is going to be, because you don't really want to have something that is 1 meter structure. You want to have something very, very compact, and we need really to try to build that. So these are some of the problems. Then of course there is the problem of the energy, power consumption of all these devices, and also the non-linear response of each of these elements if you consider practical models. So these are some of the problems that people are that should be considered, at least from the practical point of view. But the prototype, more or less, with relatively simple devices, already shows that something can be done. So that's what this is if you apply it to the transmitter. If you apply it as a processing device in the network, then there the problem is how to acquire the channel state information. how to make sure that you can estimate the channels and then you can optimize the structure accordingly. We have a paper on channel estimation for RIS, but they needs to be, I mean, it may take a lot of overhead because now we have many variables to optimize. So that's could take a little bit of time and complexity. So these are the things that comes to my mind at the moment. So I hope more or less that the answer was okay. And then we have another Alex. Regarding SIM, there is an extra physical implementation problem compared to reflective. The your meta surface layer need high magnitude transmission and tunable magnitude transmission and tunable phase. In the microwave prototype you showed, did you use a regular metasurface topologies loaded patches or something more special? Yeah, that's a very good point. So now, I mean, the implementation is not my main specialty. So I know that you are an expert in implementation, but the device that they actually implemented is not, I mean, sophisticated. So this is basically based on conventional technologies. So there is nothing much sophisticated. So each layer is composed by three sub-layers. As you can see here, you have one receiving layer, you have one ground layer, and then you have one radiating layer. This is one of your unit cells, and you have your diodes. So you have diodes that allows you the reconfigurability. So in principle, this is based on conventional technologies. Essentially what you need to build a RIS, a SIM is a transmit array. So you can use the same technology as transmit arrays that have been implemented, but then you need to stack these transmit arrays. That's essentially what you need to do. So in another paper, my colleagues explain how this transmit array can be the single layer. So the transmit array is built, what the structure of the unit cell is, and then in the paper with me and other collaborators, we have the stacked version. So the technology, to the best of my knowledge, I mean, thanks to the meetings that we had, is based on conventional basically technology. There is nothing truly sophisticated. And as I said, it's 1 bit, so we can only control the phase and only 180 phase shift. So the phase difference is 180 degrees more or less at the frequency of interest. That's essentially what we have. So that's essentially what I can tell you. I mean, but it's not you know, it's a really a regular type of implementation for a transmit array. And so I hope that more or less the answer makes sense. And so thank you, everyone. Thank you, everyone. Another question from Alex. So you have TX, RX in each layer in this program. So you mean RX, TX, transmit, I mean, modules. I mean, you don't really have modules. So you have no, instead you don't have a transmission and reception modules in each layer. You basically have a structure that looks like structure that conceptually looks like that. Each layer is made by 3 sub layers to implement the transmission, but you don't have a transmission and reception modules. This is all done through the changing the phase shift of the elements with a 1 bit quantization. So there is no RX-TX modules at each layer. Yeah, that's I mean, yeah, for sure. So thanks also for that. And okay. So yeah, Richard, we have another question in the intro with the surrounding grid frame. Yes, around Tx and Rx, you read multiple components and due to the loss. Does the Rx has to be in the near field to obtain a higher rank? Always also in the near field. Good point. This is in the near field. You would get some angular diversity of the multipath component from the risk compared to loss component. In that way, the distinguishable path and we may get higher rank, yeah, but I'm not sure this is possible in the far field where there is model. Yes, okay, that's good, very good point. So I got the point. So that's very good point. So yeah, that's a very good point. So yeah, I was giving a class on that earlier today before this
I think,
meeting.
Marco, can you hear me? I think you show in one of your slides that the same risk can provide the condition for near far. Am I right?
Yeah. So that's essentially yeah, exactly. So that's essentially the point. So Richard was actually referring to this if I got it right. So there are basically two comments that essentially as Abed was saying. So when we need to distinguish the two cases, we are in the far field or we are in the near field. So let's assume that we are first in the far field. So this multiple antenna transmitter is in the far field of a multiple antenna receiver. If this multiple antenna transmitter is in the far field of a multiple antenna receiver, and if we don't have these surfaces that surround the antenna elements, and the channel is line of sight, so it's impossible to get spatial multiplexing gain. So the rank of the channel is equal to 1. Because we have in a line of sight MIMO channel in the far field, impossible to get spatial multiplexing gain. So in that case, we are in the far field. Then what we could do is to add these basically reflectors around the artificial scatterers around the transmitter, and we may move from a line of sight MIMO channel to a multipath rich MIMO channel. At that point, the rank of the channel would be greater than 1 thanks to the artificial scatterers that we created. That's essentially one of the points that I was thinking about when I was referring to that. So what basically Richard is saying, yes, we really need to in this case was a solution to make a line of sight channel non multipath rich. In principle, if we are in the near field, and we have a multiple antenna the transmitter and multiple antenna the receiver, then I mean we may get spatial multiplexing gains even without using this device, this IS elements. But at that point, we need to optimize appropriately the locations of the antenna elements. This according to what is called the Rayleigh criterion, which is basically what Richard was saying. The chat, I need to go. About these distinguishable paths. So by spreading apart the antenna elements, we can basically get an higher rank, because we can see each antenna can see the others under different angles, basically.
Sorry, yeah, that is the kind of near field still. I mean, if they're really far field and you have still many antennas, don't they all see the same angle? I mean, in a non-scattering environment with just line of sight. So that's what's my question here. When you add this frame or around, yeah. so you still have to be in somehow a near field, otherwise you can get the angular separation here.
Yeah, no, I think that so I think that it depends basically on the
I think it depends to the distance between the layer. In one of your slides, you show the table in which the distance between the layer can satisfy both the far and near field communication, in my understanding.
Yeah, but this is a multi-layer structure. Yeah, I understand what you mean. But here we have this structure that there is not here a multi-layer, it's just a bunch of scatterers around these multiple antenna elements. Based on my understanding, what basically Richard is saying, it depends on how good you are able to create these. So I mean, how good you are in creating this multipath, because it's true that you have the line of sight, but then here you do plus and loss. It's like if you are creating a sort of Raysian fading channel. It depends on how much multipath you can create, such that you can get a rank basically greater than 1. So that's basically the point.
But you have to physically separate them. So essentially, you see these multipaths in some different angles. Otherwise, they blend in, I would assume, to the direct path.
Yeah.
So somehow this surface creates a physically larger from the point of view of the receiver.
Correct.
I suppose.
Yeah. That's correct. Okay. No, it's essentially correct to what you say. So that's correct, because in fact now I was giving you an example. There is this example on the book from David.
So I was thinking, otherwise this would be very nice for a satellite, but then the the kind of wreath here would be very large. I mean, if you have a very large distance, then I guess you get into trouble here, or?
Yeah. That's basically true. It basically depends on this angular basically spread. There is not this example from the book of David Say, for example, where you have your multi-antenna transmitter and then you have a scatterer, and that is located somewhere. And if basically what you have is that now one path that goes from the transmitter to the receiver, then you have another path that goes from the transmitter to the scatterer to the receiver. This could be 2 paths. In principle, you could have a rank equal to 2, provided that the angles under which the transmitter see the receiver and the transmitter see the scatterers are sufficiently different. And there is a formula there that allows us to compute this difference. Here, you need to surround somehow these devices in a way that you can create this angular spread that basically you were mentioning. Of course, if you don't do that, then the rank will always be equal to 1. At that point, you just get some beamforming gain that is due to the more elements that you have. That's essentially what you have.
Then I get it too. So unfortunately, it doesn't work, let's say, on a cell edge or for a satellite where it's very far. Then okay, you get the power gain, but not the diversity.
Exactly. Then, I mean, we could try to see what happens if you deploy this at the transmitter, at the receiver. I don't know whether this can be fast, this can be help, I mean, somehow. But yeah, you are totally right. So this is essentially the kind of trade-off that needs to be studied. Yeah, you are totally right. Yeah.
Thanks.
Totally agree. Yeah. No, thanks for the question, because that's very interesting, and one of the things that should be studied, I mean, deeply. Yeah, that's the point. Okay, so I guess that I'm not sure if there are other questions from the audience, but if not, so thank you very much for the opportunity and also for the many, I mean, and interesting questions and discussions. It was very, very useful. I think that we try to identify quite 10 to 20 papers, I mean, to be developed, to be worked on. So thank you very much.
Thank you very much, Marco, for the presentation and everything.
Yeah. Okay, guys. So thank you very much for joining. Enjoy. Yeah. Have a good night. Have a good afternoon.
Have a nice afternoon, everyone.
Goodbye. Bye.
Thank you.
Bye. Thanks,
Bye-bye.
Alex.
Bye.
Thanks, everyone. Bye. Bye.